Welcome all of you. In this lecture, we are going to see what is meant by constant error and what is meant by proportionate error. Now, depending upon the effect of systematic error on analytical results, there are two types of errors, that is a constant error and proportionate error. So these are actually classified on the basis of effect of systematic errors on analytical results. The constant errors are also called as additive errors. These are also called as additive errors, right? Now the constant errors are those errors in which absolute error is independent on sample size. That means in this constant error, there will be no effect of sample size on the absolute error. So absolute error will not change upon change in the sample size. However, relative error increases as the sample size decreases. That means in constant errors, if you see the absolute error, that is xi minus xt, this is the absolute error. So this value will be independent on sample size. Whatever sample size you are taking, it will not change the absolute error. But if you see xi minus xt divided by xt, that is a relative error, xi minus xt divided by xt. This is a relative error. If you want to see in percentage or parts per 100, it becomes xi minus xt divided by xt into 100. So this value actually increases as the sample size decreases, right? So to elaborate this, we need to see one example. So let's see example. So for example, suppose 500 milligrams of precipitate, which is slightly water soluble. Now this precipitate, for example, is water soluble, and when you wash it, for example, with 100 cm cube of distilled water, and during this washing, say for example 0.5 milligrams of precipitate is lost. So for example, what you are doing, you are washing the precipitate. You have a 500 milligram of precipitate, which is slightly water soluble. Now you are adding or washing with 100 cm cube of distilled water. When you use 100 cm cube of distilled water in this washing process, for example 0.5 milligram of precipitate is lost. So the precipitate should have a 500 milligram. So 500 milligram is a expected value, but when you wash it, you are losing 0.5 milligram. That means a final weight of precipitate will be less than 500 minus 0.5 milligram, that is 499. That is a 499.5 milligram, right? So this will be a final weight of the precipitate after washing, because you are losing 0.5 milligram in each step, for example. So absolute error would be of 499.5, that is observed value, this is the experimental value, minus true value. True value is a 500 milligram because you had 500 milligram precipitate. So 499.5 minus 500 milligram, you will get minus 0.5 milligram as an absolute error. That is, in this case 500 milligram is a xt here, and 499.5 is observed value or experimental value, right? After washing, you are getting 499.5 milligram. So this is your final observed value, and 500 is your true value, right? So you are getting minus 0.5 mg as an absolute error. Now if you divide this minus 0.5 by the true value, that is 500, you will get the relative error. That is, the relative error is equal to absolute error divided by true value into 100 in percentage. So 0.5 into divided by 500 into 100, you will get a 0.1% relative error. So this is a relative error, right? Now for this is 0.1% error is a nominal error, very simple. You can tolerate. So 0.1% error can be tolerable. But for example, if you have a 50 mg, only 50 mg of the precipitate, and you are washing that 50 mg precipitate with 100 cm cube of distilled water. Now in this case, your sample weight is decreased from the 500 milligram to 50 milligram. Now in this case, what will happen? We have to see. So absolute error is equal to 0.5 mg, because whenever you wash precipitate with 100 cm cube water, it is losing 0.5 mg of that precipitate. So whatever loss of precipitate is 0.5 milligram. So absolute error in this case is a constant, that is a 0.5 milligram, right? But the relative error will change because the sample weight now or sample size is decreased in this case. So relative error is 0.5 milligram, that is absolute error, divided by true value into 100, so you will get 1%. Now this 1% is a huge. Now this relative error is a huge and you cannot accept. So this is not acceptable that you are having a 1% relative error in the measurement. So this error of 1% may no longer be acceptable. Thus from this example, it is clear that the relative error increases as the sample size decreases. So this kind of error is called as a constant error. So this is an example of a constant error. Constant error is an error in which absolute error does not change. So here also you are getting 0.5 milligram. In previous, here also you are getting a 0.5 milligram. So in both cases absolute error was same, but relative error in this case is 0.1% when weight or sample size was 500 milligram, while when sample size is decreased, your relative error is increasing. So that means this example has constant error. This example has a constant error. Understood what is constant error? Constant error is the error in which absolute error remains constant, even though if you change or even though if you decrease the sample size, it does not change. But relative error is increasing when you are decreasing the sample size. Right? Now next is a proportionate error. Next is a proportionate error. Now this proportionate error is exactly reverse to that of a constant error. In proportionate errors, these are errors in those in which absolute error increases in direct proportional to the sample size. In this case, this absolute error, that is xi minus xt, increases in direct proportion to the sample size. So you cannot say proportionate error is directly reverse to the constant error, but here some parameters are changing. For example, absolute error is also increasing with the sample size in this case. However, relative error in this case remains constant. Now how this can happen, we have to take one example. For example, a substance that interferes in an analytical method may lead to such sample. Sometimes you have a substance which can interfere in analytical method. So you have incorporated some interfering element which is causing such proportionate errors. For example, in volumetric analysis of KCl with silver nitrate, that is precipitating reaction happens. Now, if you are doing this precipitation titration, then if given KCl solution contains impurity of magnesium chloride, for example, your KCl solution contains some impurities of magnesium chloride, then burette reading of 10 will be a measure of chloride from both the salts. So KCl has one chlorine atom, magnesium has two chloride atoms. Now two chloride ions, and KCl has one chloride ion. So the chloride ions will get increase, the concentration of chloride will get increased whenever you are increasing the amount of KCl solution, because that has a impurity of magnesium chloride. Then burette reading of 10 will be measure of chloride from both sides, both salts, and that's why if the sample size is double, now in this case if you were taking 5 ml of KCl solution previously and now you are changing it to a 10 ml of KCl solution, the chloride ion concentration will increase in the proportion of that 5 ml to 10 ml. For example, 5 ml has KCl as well as magnesium chloride concentration. 10 in 10 ml also it will exactly double the concentration of chloride, because in the same amount this impurity will also incorporate. So if the sample size is double, for example, burette reading also get doubled, although the relative error would remain the same. Now how this relative error remains same? Because relative error is a simple ratio of absolute error to the true value. Now in this case, because you have this KCl as a substance and you are the magnesium chloride is a impurity, and in this case when you divide the absolute error by this true value, the amount of KCl of course is going to increase from 5 ml to 10 ml, and now whatever increase in magnesium chloride happened will be nullified by the amount of KCl that you are increasing. Now this can be explained by using an example. So you need to take example, and we are going to solve some examples, and that will clear these things. So you need to see some examples. Thus, in a proportionate error, the relative error remains constant irrespective of numerical values measured. Whatever numerical values are measured, in proportionate error, relative error remains constant. However, the absolute error will be proportional to the sample size. So as sample size increases, the absolute error will also increase in case of a proportionate error. Now for example, this is a sample size and this is a relative error percentage. We are talking about only relative error here. So in this case, what happens, if the constant error is there, the absolute error will be constant and the relative error will increase. So in this case we are talking about relative error, and therefore in this case the relative error will increase. So whenever there is a increase in relative error, with the sample size there is a constant error, while proportionate error will be the relative error will be constant for the proportionate error. Relative error will be the constant with the proportionate error. And while this is a true value will be same for all sample size. That means the sample size, it will depend upon sample size. Right? So we can conclude that the absolute value of constant error is independent upon sample size. The absolute value or the absolute error of constant error is independent upon sample size. Absolute error remains same, but relative error increases as the sample size is increased in case of uh, constant error. The absolute value of a proportionate error is dependent upon sample size, right? Sample size uh, is influenced. That means sample size influences the absolute error actually in proportionate errors, because as sample size increases, the absolute error also increases in the same proportion. The relative error remains constant, but absolute error increases as the sample size is increased. This is very important. The relative error remains constant, but absolute error increases as the sample size is increased. So this happens in a proportionate error. So these two things are for the proportionate error, and these two things are applicable for constant error. These things are applicable for the constant error. Right. Now let's see some examples, because unless you solve the examples, you will not be able to understand what is meant by constant error and what is meant by proportionate error. So for that cause we need to solve some examples. So let's solve example. Now this is one example in which uh, we are going to solve this example. So in a volumetric, for example, in a volumetric estimation of silver nitrate, different aliquots of silver nitrate were titrated with solution of NaCl, and following results were obtained. Now these are three experiments, and you have taken 5 ml and 10 ml and 20 ml of NaCl, and for this you titrated with silver nitrate, and uh, amount of silver nitrate required to react with this 5 ml, 10 ml and 20 ml NaCl is, for example, for 5 ml it was 240 milligrams, for 10 ml it was 480 milligrams, for 20 milligram 20 ml of NaCl it was 960 milligrams. So this is a given data. Now due to error, it was found that 1 cm cube of NaCl, instead of 50 milligrams, it consumed 48 milligrams of silver nitrate. So there is an error in this measurement, and it is given that 1 cm cube of NaCl should react or should consume 50 milligrams of silver nitrate, but in this case we are getting a 48 milligrams of silver nitrate. So 48 milligrams of silver nitrate is actually reacted with 1 cm cube of NaCl, but it was expected that it will react with a 50 mg of silver nitrate. That means for 1 cm cube it should have, or it must have 50 milligrams. So this 51 to 50 milligram is a accepted value. So calculate the absolute error and relative error. Also comment on the type of error involved in experiment. So this is the question asked. Now we have to solve first what is the true value in this case. So these are all xt values, xi values, that is observed values, and we need to find out the xt, that is a true value. Now true value is given here. True value is true value. True value is equal to, for example, 1 cm cube of NaCl should be corresponding to 50 mg of AgN. So here we have 5 cm cube of NaCl. For 5 cm cube, it should be 250 milligrams. So for example, for 5 cm cube, it is a 250 milligrams. So 250 milligrams should be react with the 5 ml of NaCl solution. So this is a true value. So for example, expected weight of silver nitrate for 5 ml should be a 250 mg. For 10 ml, it should be a 500 mg. For 20 ml, it should be 1000 milligrams. Right, so these are true values, that is expected values. Now we have to find out absolute error by this data. Now these are all are observed value, as I said, xi. So we need to subtract it. So you will get the values, right? So you will get absolute error is here -10. So 240 minus 250, that is xi minus xt, is -10. 480 minus 500 is -20, and 960 minus 1000 will be -40. So these are absolute error values. Now find out the relative error. So how will you find out relative error? You just have to divide these absolute error values by simply the true value. True value is a 250. So you will get -10 divided by 250, you will get -4. -20 divided by 500, you will get again -4. And -40 divided by 1000, you will get again into 100. Again you will get -4. So -10 divided by 250 into 100, right? So first relative error is -10 divided by 250 into 100, you will get definitely -4. So this is correct, right? So in this way, if you see, as the sample size is increasing, the absolute error is also increasing. So absolute error is increasing in the same proportion to that of a sample size, same proportion, whereas the relative error is a constant, -4, -4, -4. What does it explain? What does it say? So let's go to back and see. The absolute value or absolute error of proportionate error is dependent upon the sample, while the absolute value of constant error is independent upon the sample size. Here what we see, the absolute error is definitely depend upon the sample size. As the sample size is increasing, the absolute error is increasing. That means the absolute error in this case is depend upon the sample size. whereas the relative error is constant. So where is the relative error is constant. So the proportionate error are those in which absolute error increases in direct proportion to the sample size. However, relative error remains constant. We have the same equation. We have the same condition that here the absolute error is increasing with the increase in the sample size while relative error is remaining constant. So we can say in comment we can say that in this case, in this example, as as absolute error increases with the sample size with sample size and relative error relative error is a constant. So this is another example. Let's just solve this example. We will see and we will comment on the type of the error present in this condition. So in a gravimetric estimation of barium as barium sulfate, the following results were obtained if the sample contains 15%, the sample contains, if the sample contains, so it should have a 16% in this example. It should have 16%. If the sample has a 16% of barium, right? So if the sample contains 16% barium, calculate absolute error and relative error. Mention which type of error present. And given we have barium atomic weight is 137.3 and barium sulfate we have 233.3. So these values are given. We have these are experimental values. For example, weight of sample, that is 1000 milligram, 2000 milligram, 3000 milligram, and in these samples we have a barium sulfate calculated. These are values of barium sulfate in milligram: 276, 548 and 820. So these barium sulfate is present in these different weight of samples, and you have to find out the absolute error, you have to find out relative error, and also you have to mention which type of error is present in this solution, in this example. Now to solve this example, always we need to find out what is the true value, because these are all expected values. These are all experimental values, that is xi. So these are weight of samples, these are xi values, and we need to find out the expected value. We need to find out the expected value. So how do we find out the expected value? So it is given here that if the sample contains 16% of barium, that means the sample should have contained a 16% barium, and this is a true value, that is the samples contain a 16% of barium. Now As the sample contains 16% of barium and we have these weights of samples, we need to find out what is the amount of barium present in 1000 milligrams of sample. And after that, for that sample, we are going to convert that barium to the barium sulfate, and then we will find out finally the expected weight of the barium sulfate. So we can easily find out the expected barium, just single barium, in this weight, in these different weights. How do we find out? Now, for example, it is given 16% barium. So, for example, for 100 milligrams of sample, it contains 16%, that is 16 milligrams. We are converting this 16%, 16 milligram of barium, and then 1000 milligrams of sample contains how much barium? So it would be nearly 160 milligrams of barium. So this is 160 milligram. This is a true value for barium. This value we have to convert to barium sulfate. How do we convert this value? So we need to find out how much barium sulfate will be there for the one will be there, or how much barium, 160 milligram of barium is corresponding to how much barium sulfate. So we have 160 milligram of barium, and also we have these different values. So from this given values, for example, 137.3 milligrams of barium will be present, or will corresponding to, instead of present we will say will be corresponding to 233.3 milligrams of barium sulfate. Right from this information, we can definitely say that 137.3 milligram barium will be corresponding to 233 milligrams, 33.3 milligrams of barium sulfate. We have for 1000 milligram we have 160 milligrams. So we have 160 milligram of barium. For this we will have double, 320 milligrams of barium, and for this we would have 3 times, that is definitely 480 milligrams of barium. So this value we have to convert into a barium sulfate. So we have 137.3 milligram barium, which will be corresponding to 233.3 milligram barium sulfate. Then for 160 milligrams of barium, we need to find out how much barium sulfate will be there. So it will be 160 into 233.3 divided by 137.3, and it will be equal to around 272 milligrams. So expected value for the barium sulfate for 1000 milligram would be 272 milligrams. Then in the same way, if you calculate for 2000 milligram. For 2000 milligram, we will have 320 milligrams of barium, and that barium will be corresponding to 500, for example, 44 milligrams. How do you find out this? In the same way, you can easily get the example. For example, it would be, instead of 160, you just put a 320 value and solve this, you will get this value. So instead of this 160 here, you just have to put this values. Instead of this value, you just have to put this 480. You will get the values, right? So it is a for 3000 milligrams of weight sample, it would be 480 milligrams of barium. So that barium will be corresponding to around 816 milligrams of barium sulfate. So these are expected values, that is a true values, that is xt. Now we already have these observed values. Now just we have to calculate the xi minus xt. For this example, there is a difference. So 276 minus 272 will be equal to 4.0. 548 minus 544, it will be 4.0. And 820 minus 816 will be equal to 4.0. So these are absolute error values, while that of for relative errors, you just have to divide by 272 into 100. You just have to divide this by the true value. This is a true value, and you will get 1.47 value, and you will get 0.74. After calculation, you will get 0.49. 0.49. So from these results, you definitely see that in this case, as the sample size is increasing from 272 to 860, the absolute error remains constant. It definitely remains constant, but the relative error is decreasing. That means if you are decreasing the sample size, you are increasing the relative error. If you are increasing the sample size, you are decreasing the relative error. So tell me, what kind of error is present in this example? Yes, you are right. This example has a constant error. So this example definitely has constant error. So in previous example we had proportionate error, and in this example we have a constant error, right? So in this way we can definitely find out which error is present in given example. So we will stop here. We will meet in next lecture. We will talk about accuracy and we will talk about precision. We are going to see how precision is determined for given set of data, and we are going to see what are the different terms which are useful in order to find out the precision of the given method. So we will stop here. Goodbye.